Okay, so this is what I wrote down at the end of the last clip. This is for the total number of modes in the cavity, and I just wanted to say that I forgot the 3/2 here. Okay, just got to put that in there. So this quantity, this argument here, nx squared plus ny squared plus nz squared is equal to 4a squared over lambda squared. So when you multiply all this together, what you get is that the total number of modes in the cavity, okay, cavity of side length a, is equal to 8 pi times a cubed divided by 3 times lambda cubed. Okay, so that basically tells you that the number of modes at a particular wavelength lambda, okay, is this. All right, and we see that as lambda gets bigger, the number of modes goes down, and that makes sense because as lambda gets bigger, that means that there's you have trouble fitting in modes into the cavity because the wavelength is getting closer to the size of the actual cavity itself. So, for example, when lambda is equal to a, okay, then you only have 8 pi over 3 modes. When lambda is equal to you could plug in what happens when lambda is equal to a over 2, okay, and you're going to get fewer modes. Okay, so now we need to go back to, so now we've finished with the first part of this derivation. That is, we've counted the number of modes inside the cavity as a function of wavelength, basically. And now we want to determine the number of modes per unit wavelength and determine the energy per unit wavelength per unit volume. Okay, so the way that we determine the number of modes per unit wavelength, okay, so now we're on 2, is that we just take our expression for n and we differentiate it with respect to the wavelength. Okay, so this is just d by d lambda, so lambda of 8 pi a cubed divided by 3 lambda cubed, and this is, if you do the differentiation, is equal to minus 8 pi a cubed divided by lambda to the 4th. Okay. Now the negative sign just reminds us that the number of modes decreases with increasing wavelength, as I said before. Okay, and furthermore, we can get partway to step 3, where we're trying to determine the number of modes per unit, the number of energy per unit wavelength per unit volume, simply by dividing this expression divided by the volume of the cavity, which is just a cubed. So if we take dn d alpha times 1 over a cubed, okay, then we get obviously 8 pi over lambda to the 4th. Okay, notice that the negative sign went away just because we're interested in the magnitude, and this again is basically the number of modes in the cavity per unit wavelength per unit volume. Okay, so now if we basically, in order to find the number of the energy per unit wavelength per unit volume, okay, then we basically just have to figure out a way to assign an energy, an average energy for each one of the modes. Okay, and this is where actually Rayleigh and Jeans went wrong. Okay, this is well, they basically did something reasonable, but it required an understanding of the quantization of light in order to make the right thing. But let's just go through what they did.